So today's topic is data analysis. We've been kind of continuing that topic for the whole unit. And we're going to start by finding the range and the interquartile range. So the range is your max minus your min. So you should have had 67 minus 7, and you should have found 60. And then your interquartile range is your third quartile minus your first quartile. So remember that the quartiles are like the midpoints of each half. So the median splits your data in half. And then the first half of the data, you can split that in half, and that would be your first quartile. The median is technically your second quartile, but we call it median. And then your third quartile is the middle of your second half of data. So it's basically like that 25% mark and that 75% mark. Okay, so if you subtract those, then you can find your interquartile range, and you get 19.5 minus 11, and that would equal 8.5. Did you guys get those numbers?
Yeah.
Okay. All right. So it says identify an outlier, and they're just kind of asking you to use your intuition here because we haven't defined outlier yet. So which one looked like an outlier to you? 67 definitely looks like an outlier because it's far from the others. And so then it says to recalculate with the outlier removed. Now that's super easy to do in your calculator because you can just delete the 67 and then run the values again with the one variable statistics. But by hand, you would just take it out and then find your median again and then find your quartiles again. But for your range, it's just going to be 25 minus 7 to get 18. And when you recalculate your quartiles, you should get 19 minus 11. And that would give you 8. So these are two different ways of measuring how spread out a data set is. And you can notice that the outlier affects which one more, the range or the interquartile range? The range, right? Because the range was 60. And when we eliminate the outlier, it's 18. That's a huge difference. For the interquartile range, when we took out the 67, we just went from 8.5 to 8. It was not a huge difference. Okay, so outliers really do affect the range. Any questions on that? All right. So let's read about outliers because we're going to get a better definition than just using your intuition as to which one might be an outlier. So we've seen that outliers are extraordinary data that are separated from the main body of the data, but so far we identified them informally. So a common test to identify outliers involves the calculation of the upper and lower boundaries. So that's going to tell you like your data should be within these upper and lower boundaries. The upper boundary is the upper quartile. Oh, here's two wrong ways to spell quartile. So one wrong way is quartile, and the other one is quartile. The right way to spell quartile is quartile. So the upper boundary is the upper quartile plus 1.5 times the interquartile range. The lower boundary will be the lower quartile minus 1.5 times the interquartile range. And that will tell you about where your data should be. So if you have something outside of that, we're going to call that an outlier. Outliers are marked with an asterisk on a box plot. And there might be more than one outlier at either end. Each whisker extends to the last value that is not an outlier. So let's see how that's going to look. Let's turn the page. All right, the first set of data, we're not even going to draw the box and whiskers plot. We're just going to identify outliers. So let's take a minute and put this data set into the calculators so that we can find our first quartile and our third quartile. All right, so once you have that data in your list, you can go to stat calculate one variable statistics. And I don't have a frequency list, so I'm just going to calculate. Okay, so I see my first quartile. I'm going to write that down. I'm going to write down the min too. So min is 1. First quartile is 6.5. And then, how do I go down over here? It's the median. Okay. So the median is 8. The third quartile is 10. and the max is 16. I don't know if I need all those numbers, but if I were making a box and whiskers, I would want all those numbers. Okay, so we need to find the interquartile range. So that would be the third quartile minus the first. So the IQR is going to be 10 minus 6.5, so 3.5. And then we're going to use those formulas from the previous page. So we're going to find the upper bound, upper, by doing the third quartile, 10, plus 1.5 times the interquartile range. And then we're going to find the lower bound with the first quartile, 6.5, minus 1.5 times the interquartile range. So go ahead and calculate that, and that should tell us if we have any outliers. All right, how many outliers do we have? 16 is an outlier. Are there any other outliers? So 3 is not an outlier because it's between 1.25 and 15.25. But yes, 1 is an outlier. So the outliers are 1 and 16. Tell me more about 3. You seem convinced.
On my calculator, it's 10 minus 1.5, and then in brackets 3.5, and I got 4.75.
Oh, so for this one, for the lower, you use the first quartile.
Oh, okay.
Yeah, it's a good question. All right, any questions on that? So it's a pretty easy technique to figure out where your data point should be so that you can identify your outliers. All right, so for the box and whiskers plots, you need the minimum, the lower quartile, the median, the upper quartile, and the maximum. And like I did that here, but now down here it's telling you that's what you would need, okay? For the maximum though, you're not going to, and for the minimum, you're not going to use outliers. So like if I were doing the box and whiskers here, then I would cross these out and I would replace them with what? Besides 1, what's my minimum? I think you're right, 3. And then besides 16, what's my maximum? 14, yeah. So when you're doing your box and whiskers plots, the 1 and the 16, those would be asterisks. And the 3 and the 14, those would be the ends of your box and whiskers plots. Okay. All right, interpreting a box plot. So when you have this data, which has what kind of distribution? Is that negatively skewed, positively skewed, or symmetric? It is symmetric. So a set of data with symmetric distribution. We'll have a symmetric box plot. Okay, so if I'm trying to get this data set into a box and whiskers, I'm going to expect that the box and whiskers will also be symmetric. The whiskers of the box plot are the same length. The median line's in the center of the box. That would be a symmetric box plot. If a set of data is positively skewed, then it will have a positively skewed box plot. All right, so this side we have a negatively skewed graph, which makes a negatively skewed box and whiskers. Okay. All right, so it says to find the 5-number summary and then draw a box plot for it. So I want you to start by finding that 5-number summary in your calculator. 5-number summary again is min, quartile 1, median, quartile 3, and max. It's nice to write them all together, but I kind of ran out of space. I think we are just assuming that we have no outliers for this problem, but if you want to verify that, that's great. It just doesn't seem to be something that they're asking in this problem. So go ahead and put those in your calculator. So I got the minimum is 2. First quartile is 2.5. Median is 5. Third quartile is 6. And maximum is 9. Does that match what you got? Okay. All right, so to draw this, we need a number line. Your number line should be somewhat evenly spaced. I mean, we're not perfect, but we can try to be perfect. So we're gonna need numbers at least between 2 and 9. I'm gonna start at 0. So I got 0, and just try to go evenly spaced, adding up to at least 9. Yeah. And then personally what I do is I just make a dot at each of these numbers just to remind myself like where they are. So 2, 2.5, 5, 6, and 9. And then I use that as a structure for my box and whiskers. So the box is the middle 3. And then the whiskers go on the sides to the other ones. So something to keep in mind about the box and whiskers plot, hopefully you drew a prettier one than me, is that the median means that half the data is on this side and half's on this side. The first quartile means that half of the half is over here, and it doesn't look like it, right? Like that looks really small, but that just means that the spread of the first 25% of the data is really small. We have a lot of numbers between 2 and 2.5, okay? So there are a lot of numbers in there, and they're just not spread out. This is also 25%, this is 25%, and then this is 25% of your data, because we cut your data set in half, and then we cut each half in half. So now you are going to find these values: range, interquartile range, and then we're going to find the percent of data values which are less than 3. How are we going to do that? We'll figure that out in a sec. Do we get the same values for range and interquartile range? Okay. And then it is possible to find the percentage of data values less than 3, but that's not something we've learned today, so we're going to do this problem instead. The percentage of data values which are less than 2.5, because here's my 2.5, and so I'm talking about this piece right here, which is what percent? Is 25%, right? All right, box and whiskers plots are particularly useful when you see 2 box and whiskers plots next to each other. So for example, if you saw a distribution of scores on the SAT versus a distribution of scores on the ACT, you could see like which one maybe has like a bigger interquartile range, or which one has a smaller minimum or a larger maximum. So those would be useful to look at. Let's turn the page. So in number 3, we are going to be comparing different anesthetics. We want to see how long they take. So we have these 2 lists of times, and we're going to draw a parallel box plot. So you're going to put each list in to the calculator, and you're going to find your 5-number summary for each, and that's going to take you a minute. So while you guys do that, I'm going to help you get set up with how quarter. Somebody who did the old drug times, can you tell me what you got for upper and lower bounds? 19.25, and the other one? 3.25? Okay, and then somebody who did the new, can you tell me what you got for your upper and lower bounds? 13 and 5. Okay, so for the old, do we have any outliers? So the old 21 would be an outlier. Is that the only one? Okay. So that means our maximum is now, what's the biggest one besides 21? 16? Okay. And then for the new medicine, are there any outliers? For the lower quartile here, it should be 1.25?
I also got
1.25? Okay, thanks guys. Yeah. And Sammy's agreeing too. 1.25. Okay. So that means there's no low outliers, right? So we just have 21 as an outlier. And then over here, do we have any outliers? No. Okay. All right. So here's how it's going to look. We're going to use 16 as our maximum for the old one, and we're going to use 5 for our minimum. And so I'm going to mark 5. We're going to need space to put one box plot above the other. So I'm going to put the old one lower. I'm going to put 16. And then I also need to mark 8, 10, and 12.5. So 8, 10, and 12.5. And I'm going to make a short little box in here because I need space for the other box. I don't know why I'm so bad at drawing boxes today. Okay. And then we're going to put an asterisk for the outlier. So the outlier was 21. And so we can just put like a little star. I'm going to use a different color for the other one. So the new one has 7, 8, 9, 10, and 12. So this is new, and then this is old. All right, so think to yourself for a minute, like what would be the benefit of this new medication? The medication is to put the patient unconscious before okay. Raise your hand if you have an idea to share. I should be seeing lots of hands. Ava? Yes, very good. Smaller range means more precise. Very good. All right, so let's add that here. The new medicine is more precise. It'll be easier to predict how long it will take to work, because it has a smaller range and a smaller IQR. New medicine is more precise, easier to predict how long until it works. Questions? Okay. Let's take a 1-minute brain break, and then we're going to move on, because we have to talk about these cumulative frequencies. All right, when we want to know, just a reminder, let's put phones away. When we want to know the proportion of scores that lie above or below a particular value, we can add a cumulative frequency column to the frequency table and use this graph called the cumulative frequency graph. Is it frozen? Yeah, thank you. The frequencies are plotted and the points are joined by a smooth curve, and it differs from a cumulative frequency polygon where you use straight lines. So there exists something where you use straight lines, but we don't have that. We're using this one with a smooth curve. Let's turn the page. So the percentile is the score at which a certain percentage of data lies. So for example, when you take like a PSAT or an SAT, they'll give you a score, and often they'll tell you like what percentile you're at. Like for example, like 67% of students scored less than you. So that would put you at the 67th percentile. And so they gave you more examples of that right here. And they just are reminding you that the lower quartile is the 25th percentile. The median, of course, is the 50th percentile. That means 50% of people scored less than you. And the upper quartile is the 75th percentile. And you can show this, you can demonstrate this in a cumulative frequency graph. So we're going to calculate cumulative frequencies here, and it's really quite simple. All right, so the first interval we have is 146 to 148. These are results of the women's marathon. And there are 8 people in that interval, and so far we've seen 8 people. That's it. Okay, the next interval is 148 to 150. There were 3 women who finished in that time. Cumulative frequency would be how many women finished in this time or less. So we add, and we get 11.
So we added up.
So we keep adding. So then the next one, we're going to add 9 to 11. And then 11 to 20. 12 and 31. Okay, and continue adding these. I'll give you a minute to add them. You don't need to watch. We got the same numbers? Okay. So now we're going to represent this data in a cumulative frequency graph. So we need to label our axes. We're going to show a little break in the graph in the x-axis because if I started at 0, I would never get to 170. So the little tiny break down here in your x-axis. And then I'm going to start at 146. And we almost have enough room to count up by ones. 146, 147, 148, 149, 150. I would need one more box because I use this box up for a break. And so I just had to go outside of the grid once. Then over here, I'm going to count by 5s. So I've got 10, 20, 30. This would be cumulative frequency of competitors. And down here, I've got minutes. Okay? So take a moment to set that up. To go ask Miss Young one thing. I think that we would use the median, like we would use 147 when we're graphing these, but I don't know. All right, this makes much more sense. We do not use the middle, and there's a good reason. Okay. Oh, I recorded all that. You guys get to listen to 5 minutes of silence. All right. So there are 0 competitors that were below 146 minutes. So at 146, you're going to graph a 0. But then there were 8 competitors that were below 148. Sorry, it's frozen, right? There were 8 competitors that were below 148. So then 148 gets an 8. So 149, 148 gets an 8, approximately, of course. 11 competitors below 150. So 150, you're going to graph 11. There. Okay. So keep going on that. Remember, what we're graphing is we graphed a 0 at 146, and then we graphed an 8 at 148, and we graphed 150, 11, 150, 220, and so on. So let's go ahead and do that. All right, so mine's looking something like that. Notice that the last ones got spread out a lot more than the others. And then you're going to connect them with a smooth curve, as smooth as you can. All right, so it says on the next page to use your graph to estimate. So now we have a table. There are other ways to find these things, but it's asking you to practice using a graph to do these estimates. So the first thing we're estimating is the median finishing time. So my first question for you is, how many competitors were there in this race? There were 69 competitors in this race. So remember, to find the median number, we learned this last class, you add 1 to the number that you have, and then you divide by 2. So on the next page, that's what I'm going to do. So we have 69 plus 1 over 2 means I'm looking at the 35th competitor. And I want to find the time for the 35th competitor on the graph. So now that we know it's the 35th competitor, turn back and let's use the graph to figure out the time. Approximately, because we're using a graph, so it might not be exact. So here's 35. For some reason, straight lines are really hard for me today. 35. Okay, so it looks like it's going down right between these two boxes. So I'm going to say my estimate would be about 134.5. Does that make sense? Do you see what I did there? I looked at the 35th competitor, and then I looked down to see what their time would be. I got 134.5. Wait, is that 154.5? I can't read my own handwriting. Sorry about that. So 154.5 minutes. The number of competitors who finished in less than 155 minutes. So that's going to be pretty close to 35, but let's look and see, because it might be a little bit more. So go back and look at 155 minutes. How many competitors does it look like to you? It's a little bit more, right? Is it like 36 or 37? All right, I'm gonna look. So I'm here. I'm actually like getting like 40. Is anybody else getting something like 40? Okay, I'm going to go with that. Looking at the way I drew my graph with a smooth curve, I'm getting about 40 competitors that were 135 or less, like that. 155. I keep reading my graph wrong. Sorry. 55. Okay, so 40. The percentage of competitors who took more than 159 minutes to complete. So we're going to find out how many took more than 159 minutes, and then we're going to find the percent. So let's find 159 minutes. Right here. All right, this is definitely in between. Would you guys want to call that 52 or 53? 53? Okay. So we said 53 are going to take less than 159, but it says more than 159, right? So 53 take less than 159. And so how many are going to take more than? I'm just going to subtract it from the total, right? 16 take more than 159. And then I need to calculate that as a percent. So that would be 16 out of 69. Can you guys calculate that real quick? Are you guys getting 23.2? Okay. 23.2%. And the time taken by a competitor who finishes in the top 20% of the runners. So 20% of 69. You just multiply 0.2 times 69. And I get 13.8. Which I'm going to round to 14 competitors, because those are people. There's no part people. So I'm looking for the top 14, right?
If you're rounding into the people, wouldn't you round down? You can't have more than, like...
You can argue that with me if you want. I'm going to round up today. So 14 people were in the top 20%. And so that means that how many people were less than them? Let's see, 69 minus 14 is 55. So we're looking for the time taken. Yeah. Wait. Oh no, because we want 14 because you want to have a low time for this. So we're gonna look for the 14th person. Yeah. So you want to have a low time in a marathon. So let's look for the 14th person on the graph. Turn back again. All right, so it's going to be just underneath that 15 line. So maybe 150 point something. 151 you like? It's close to 151. 151 or 150.8 or something like that. We're estimating, so I'll take 150. So the top 20% is 151 minutes. All right, so range and IQR are not perfect measures of spread, and so we have these others, variance and standard deviation. The population variance is this formula. It looks a mess, but it's actually not that big of a deal. It says if you take every single point, so x sub I would be a point of data, and you subtract the mean from it, and then you square that number, and then you add up all of these differences from the mean, it's going to tell you on average how far your numbers are from the mean. The reason we square and we square root is because that eliminates the effect of negative numbers, right? So if I had like a mean of 5 and I was doing 2 minus 5, I would get -3, and I did 8 minus 5, I get -3, and I would get +3, and I would add them up and I get 0. And that would make it sound like all of my numbers are 0 away, and that's not true. So by squaring the number, it gets rid of that negative, and then square root will undo the squaring.
What was the fancy E?
Over here,
Yeah.
sum. So that means find all of the differences from 1 to n. So like if I had 10 terms, then I would subtract each one minus the mean, and I would square it, and then I would add up all my answers, and then divide by how many there are. The good news is we don't really have to do that because your calculator will do it for you. But it's kind of nice to know what your calculator is doing so you understand like what it is you're actually finding. Okay? All right, so this is variance. Let's look at the next page. And we also have the standard deviation. Now notice the difference between the variance and the standard deviation is the square here. So the variance is the square of the standard deviation. However, there is a better method for calculating the variance than actually just squaring the standard deviation. There are some inaccuracies that will come up if you use that method, which we talked about last class, but there's a better way to do it. If we are given a sample, then we calculate the sample variance as opposed to the population variance. So here are the calculator directions for finding the standard deviation, which we did this last class. Like every time we find our one variable statistics, it shows us the standard deviation down here. So we found this last class when we were working on those IB questions. So that's not new. You enter your data in your lists and and you do your one variable statistics. But we're going to learn a new way to find the variance at the bottom of this page. So we need a data set. Maybe it's on the next page. We're going to enter a data set. Let's enter that data set for number 5 so we can try to see if we can find the standard deviation and the variance. Okay? So turn the page. And let's all do this now. Everyone should have a calculator on their desk, and let's all enter the list about a sample of 30 spectators at a rugby match. Check on your neighbor. If your neighbor is not touching their... So, I mean, variance literally means how much the data set varies. And so it's like the average difference between each point and the mean. All right, next one. The next one does not say the word sample in it, so we're gonna assume that is what? Population, okay? So for population, you are going to use this one, and then this one, okay? So let's go ahead and find the variance, and then, find the standard deviation and then the variance. Oh, we're going to use the midpoint for these, okay? So we need to calculate the midpoints. For example, the first one, midpoint is 4.5, right? Okay. Oh, and we have a frequency, so this is a different problem. They're pretty much all something 4.5, right? Okay, don't forget to enter your frequencies in list. All right, so what we did was we put the midpoint of each range on list 1 and the frequency in list 2. And then we're gonna go to stat calculate and one variable statistics. But this time, after you press enter on list 1, we need to enter list 2 for your frequency, and that is listed above number 2. So you're going to press second 2 to get list 2. and then you're gonna calculate. All right, so we get the standard deviation is 16.8. Let's see if that works for us. All right, so we're gonna press VARS, and we're gonna go to statistics again. All right, and then Kaden points out this is the one that looks like what we want, so we're gonna press 4, enter, and then we need to square that one, which is like really close to what we had before. And then we're gonna square that one. And I'm getting 282, which is right. So that is